Chapter 2. So I'm giving a summary, just a summary, not the whole thing, not every little detail. Still read the book, and I'm using the OpenStax physics textbook just as a reminder. And I'm going to try to stick with their notation for the most part. There is one small deviation that we're going to make. But anyway, this is Chapter 1. Chapter 1, just as a review, what did we talk about in Chapter 1? We said, what is position? What is displacement? What is the average velocity? Right? So we define the average velocity as the rate of change of position. So it's the change in position with respect to time. Delta means change. But we can also write the average velocity as the initial velocity. Actually, they write this, they would say this is V0 and just V. V0, the initial velocity plus the final velocity divided by 2. And that works in many, but not all cases, but it would be fine in this class if you say it always works, even though it doesn't. And then we define acceleration as the change in velocity with respect to time, again, change in. And then using these alone, we can do a little mathematical manipulation, and we get these equations. So these are the three primary kinematic equations. This is the final position is the initial position, initial velocity time, 1/2 acceleration time squared. And this for the velocity, initial velocity A, acceleration times the time. And then this one is a relationship without time. And we did say A equals negative G, where G is 9.8 meters per second squared. This is what we're actually the gravitational field. And if an object's moving up and down under the influence of gravity, which we'll get at gravity as a force later, then it has this is the acceleration negative G. We call G positive because it's actually a magnitude of a vector. But, okay. So, let's talk about two-dimensional motion. Okay, and I want to present the following situation. Okay, I'm going to give you instructions. So I want you to move 2 meters, let's say even 3 meters. And if you don't like thinking about it in meters, that's fine. I'm going to use meters, and you can always picture a meter stick in your head. It's not a yardstick. They're a little bit different. Okay, it's got meters and centimeters on there. But imagine that you move 3 meters, and then you move 4 meters. So stand on the floor. And in fact, if you do it on a floor, my floor has 1 foot squares on them. And if you want to do feet, that's fine. 3 squares and then move 4 squares. Now, the question is, how far are you from where you started? So you start at point A, you go to point B, and then you go to point C. So this is A to B, B to C. So how far is it from A to C? How far have you gone? If you said 7, you're correct. If you said 1, you are also correct. If you said anything between 1 and 7, you are correct. And that's because when we think about motion in 2 dimensions, we can't represent them as just numbers. So let me go ahead and describe for you what's called the position vector. But I'm going to draw this picture first, and then we'll talk about the position vector. So imagine that I have point A right here. That's where you start. And now I'm going to move 3 meters. Right there. That's point B. And then I'm going to move 4 meters. That's point C. So this is 3, and that's 4, and that's C. So how far away are you? Well, you're 7, right? It's pretty easy. That's pretty easy. Okay. Now, I could also do this. What if I did this? I would move 3 that way, and then 4 this way, and then C is over here. Now how far am I? You see, it's not so easy. I'm going to go 3 that way, 4 this way. I'm actually only 1 meter away from where I started. Now let's do one other case that we could calculate. Imagine that I go here, 3, and then I go up 4. How far is this? Well, if I took a right turn here, that's a right triangle. That's kind of nice, right? So in a right triangle, I can say this distance, which I will call, let's call it just S for now. I can say S squared is 3 squared plus 4 squared, right? Because that's the Pythagorean theorem that works for right triangles. So this is going to be 9 plus 16, 25. So s squared is 25, so s would be 5. So that one's easy. Those are the 3 easy cases. Now, I could also do something like this. I could go 3, I didn't even draw it correctly, 4, how far is that? That one's more difficult. Now, I've seen a lot of students that come from high school and they say, aha, you can use the law of sines and cosines. Yes, you can, but just don't. Just don't do it. It's not going to be worth it, because although you can do that in this case, once we get to more complicated cases involving more than 2 motions, no work. Okay, so how do we deal with this in a generic sense? This is where we are going to have to introduce the idea of a vector. We kind of used one-dimensional vectors before in the last chapter, but now want to really use them. So a vector is a variable that has more than one piece of information. And then we have a scalar. I think I said this in the last video, but I'm not sure. So we have a scalar, and then we have a vector. So you can think of vectors as things that have direction. Direction matters. So let's talk about things where direction doesn't matter. Time. You don't say, I'm going 3 seconds east. I mean, you can say it, it doesn't make much sense. Mass. What else have we seen that would be, and so far, I mean, I guess speed, but not, that's a bad one. Let's just, temperature. I'll use temperature. We're not going to really look at temperature too much, but that's one. They don't have direction, right? You can't say what the direction is for the temperature. But for vectors, the ones we're going to look at so far are position, that matters, where you are, displacement, which is a change in position, velocity, right? If I go 20 miles an hour west and 20 miles an hour east, something different is going to happen. And then acceleration. These are some that we're going to look at, but there are, of course, more. But those are all vectors. They have direction associated with them. So how do we represent a vector? Well, let's talk about what we've already done. We've already represented a vector by drawing an arrow. So we like to draw a vector. I'll call this just vector A. Let's just deal with generic vectors, and then we'll go over and talk about displacement vectors. This vector we represent as an arrow, so it starts here, it ends there, and it has 2 important properties when you draw it. The 2 important properties are how long is the vector and what direction is it. But that means that if I have another vector that has the same length and the same direction, it's the same vector. So it doesn't matter where you draw that arrow. It only matters how long is the arrow and what direction is the arrow. If I change the direction, it's a different arrow. It's a different vector. Okay. If I change the length, it's a different vector. So how do I add vectors? Oh, let me see this right away. You can see I represent, and most of the normal functioning world represents vectors as a variable with an arrow over it to indicate that it's a vector, not a scalar. Now, the textbook that you're using represents it like this, bold, which no one likes, right? That's the old way of doing vectors, is to write them as bold type. But you can't draw bold, and we draw things, so it's just easier to draw it as a variable with an arrow over it, and that indicates that it's a vector. So I don't like that notation in the book, but I'm just letting you know, I'm not going to write vectors as bold. Okay, so let's suppose that I have the following problem. Vector A plus vector B equals vector C. So here's my vector A. I'm going to draw them. Here's vector B. I'm going to draw it right there. So the graphical way of adding vectors is to take that first vector and then take the second vector, the beginning of the second vector, to put it at the end of the first vector. So I'm just going to move this vector. I can use my fingers to kind of just mark that, and I can see where I put it, so I can draw it correctly. You could measure the angles and the lengths and all that stuff. It's not terrible idea, but in practice it's not that useful. And so this is the same vector because it's in the same direction and the same length. Now I can draw the vector C is going to be from the beginning of A to the end of B, and it looks like that. I could measure the length of that if I wanted to. I could measure the angle if I wanted to, but that's that. So that's how you add vectors. It doesn't matter what directions they are. I could say, here's vector A, here's vector B, there's vector C. Anything combination works. Let's also look at how would I subtract these vectors, because that actually comes up too. So let's use those same vectors A minus B. Oh, let me show you this. Actually, A plus B is equal to B plus C. Now you may say, oh, well, that's just obvious. It's not always obvious because these are not just normal numbers, they're vectors. So vector addition does commute. If I go the other way and I take B plus A, so if this is over here, here's B, and then I add A to the end of that, I get C, and you can see those two vectors are the same thing. Subtraction, the way I can subtract things is actually a trick and that I haven't covered, and it's called scalar multiplication. So if I have a vector A, let's say 2 times a vector A, what I'm going to do is just take that same vector A right here, but it's going to be twice as long. So it's going to be, instead of this, it's going to be that, and then 2 of them. And that's my vector. That's 2A. Well, what if I take negative B? That's the same thing as the vector B, but I multiply its length by negative 1. So if I have B and I multiply by negative 1, it actually reverses the direction. So negative B looks like this. Now I can just add A plus negative B. So here I have A, negative B, and then that would be C. Another way to subtract vectors is very useful is to put the two beginning from the same point. If I have here is vector A and here is vector B, then A minus B is going to be the vector from B to A, end to end right there. So this is going to be A minus B. Now, of course, A minus B and B minus A is not the same thing. Okay, so that's graphical adding of vectors. But like I said, if you want to find the magnitude of a vector, it's kind of complicated. So there's another way to do this that makes more sense. And this is called adding vectors by breaking them into components. This is the component method of vectors. So imagine that I have two vectors again. I'm going to do this, A plus B equals C. And then here's my vector A. And then here's my vector C. B, I'll put it like this. Let's make it extreme. I'll just put it at the end. This is B. And how do I find the magnitude of C right here? And I don't know these angles necessarily. Well, here's the trick. Any vector, I can break into a sum of a vector in the x direction and a vector in the y direction. So I can take that vector A, and I can put it in my coordinate system here, x, y, and here's my vector A. This is a sum of vectors going that way plus that way. And I can call this AX, x hat, AY, y hat. So the x hat and the y hat are just notations to take this value and make it a vector. But then I can get A is equal to AX, x hat, plus AY, y hat. And this is component form of a vector. It turns out to be super useful, way more useful than drawing vectors by hand, graphically. Now the question is, how do I find AX and AY? Well, let's just talk about that really quickly. Because the key thing here is that the X and the y directions are perpendicular, so that means that we have a right triangle, and we can use right triangle trig, yay. So if I have the length of this vector A, and I know this angle theta right there, I can find the magnitude of that side right there using my cosine function. So I can say AX is A cosine theta. Because remember, cosine theta is adjacent over hypotenuse, so if I solve that, I get A. Now here I'm writing A without an arrow over it, so it's a magnitude, it's a scalar value, it's just the magnitude, the length of that vector. And then cosine theta is the angle, the cosine of that angle. And the same thing for AY. AY is A sine theta. Now, be careful. Okay, be careful because you can make mistakes. What you want to do is look at your diagram and look at, I know AY sine because there's an angle theta and it's the opposite side. Okay? I also want to check the sign of the values here. Should those be in the positive x direction, the positive y direction? In this case, yes, but it's not always the case. So make sure they have the correct sign. And we'll talk about that when we do some examples, but that's how we can find the components of a vector. Now, why would we do that? Let me switch colors here and see if we can kind of draw this. So here is my A vector. I'm going to draw that as AX, like that, and AY, like that. You can't really tell. That looks. I did orange and. Do I have blue? What about red? That's better. Okay. Y is going to be red. And I'll do green, green, and red. Close enough. Okay. Now I'm going to do the same thing for vector B. So it has a x component, like that, and a y component, which is actually negative, like that. Now I have these two vectors, and I can rearrange. I can, instead of saying A plus B, I can say AX, AY, BX, BY, but I can change the order, right? So now I can take AX plus BX, and those two are in the same direction. So I can just add the numbers if they're in the same direction. And then I can take AY and BY, even though they're in opposite directions, I'm still just adding them, right? Because one's a negative number. I can just add them. And then I will have this. I'll just start right here. I'll have AX plus BX is that. AY plus BY is that. Those two are perpendicular. I can add perpendicular values because I can use the Pythagorean theorem. So that's going to give me my x component and my y component. So let's do this in the full way. Okay, I'm going to take these two vectors. I'm going to add them. I'm going to create the components, and I'm going to add them all with just generic numbers, no numbers. And then we'll talk about how to apply that in real cases. And I'm going to have some other videos where, see, that's why I don't like those red and yellow ones, because they don't really erase. So let's say over here, I'm going to say my vector A is this, and I'll call this theta 1. And then I'll draw it just to be different. I'll put B over here. I had B was like this. And just again be different, I'm going to call this theta 2, the angle from the y-axis, just so you can see. And this is the vector B. So I can write A as A cosine theta x hat plus A, and this is theta 1, sine theta 1 y hat. So if I know the magnitude of that, I know the angle, I can find those components. B, in this case, look over here, this is my right triangle down here. So my adjacent side of the right triangle is actually the y component. My sine is going to give me my x component. So in this case, it's going to be B sine theta 2 x hat. Now, that's in the positive x direction, so that's positive. That's in the negative y direction, so this is going to be minus B cosine theta 2 y hat. And then to get my my value of the vector C is going to be equal to this plus x. They're in the same direction. So I can just say a cosine theta 1 plus b sine theta 2 x hat. And then I'll put the y hat below it. So for the y hat, it's going to be a sine theta 1 minus b cosine theta 2 y hat. So that's just a number. That's just a number. I have I'm technically done. I'm technically done finding the sum of those two vectors. I just have it in component form. Now, what if I want to find the magnitude? Well, let's just write this out as a vector. So suppose this is my vector c. Well, I can find the magnitude of c, which we can write two ways. I can write this as c with absolute value signs around it, or just c. And that's going to be equal to the x component squared plus the y component squared square root cx squared plus cy squared. Because that's just a Pythagorean theorem. Now, if I want to find this angle right here, you do have to be a little careful. I'll call that theta 3. Let's say I can use either the sine, cosine, or tangent. Normally we would use the tangent. The tangent theta 3 is the opposite, which would be cy or cx. So then you can x. So I can take the inverse tangent of both to find that. Now you do have to check because redundancy in the tangent function doesn't always work. Okay, I know that's a lot. We're going to have to practice that. So if you get overwhelmed with vector stuff, it's okay. We're going to practice it. But let's talk about the position vector and displacement. So if I go to actual positions, that was generic vector stuff. It could have been used for any kind of vector. But let's start off with actual real positions. Suppose I have an object right here with an x and y value. I can define that with what we call position vector from the origin to that location. And most places use the vector r to represent position. I'm going to use the vector r to represent position. And in this case, it's pretty easy, right? Because I can find the x and y components of this. It's just x and y. So I can say r is x hat plus y hat. That's my position vector. Now, what if the object moves? What if it goes from here to somewhere else? So let's call this, actually, what if I want to call that r1, and that's x1, that's a y. y1, x1, and then it goes over here to x2, y2, and that has a vector r2. Then I can find the displacement, which we write as delta r, and it's r2 minus r1. Now, vector subtraction, it's just like vector addition. Instead of adding the components, I subtract the components. So I can call this r1, 1, 1. r2 would be x2, x hat, plus y2, y hat, and then subtract those two. So delta r, the displacement, is going to be equal to x2 minus x1, x hat, plus y2 minus y1, y hat. So I can find the displacement. Why do I care about finding the displacement? Because if it goes from here to here, in a certain time interval delta t, I can say delta r over delta t is equal to, what do you think that is? That is the average velocity. But it's a vector. If I take a vector, if I multiply by a number, I want to multiply each of these components by that number. If I divide by a scalar, I'm going to divide each of those components by a scalar too. So actually, we can write the average velocity as v average x hat plus v average y hat, where v average x is delta x over delta t, or x2 minus x1 over delta t, just like before. So this is kind of a big deal because what we've done is to look at two-dimensional motion by turning it into two problems, an x motion problem and then the same thing for the y motion. So we have two-dimensional motion is just two one-dimensional motions. Three-dimensional motions is just three one-dimensional motions. We're not going to really do three-dimensional motion really, but the idea is the same. It's pretty easy to go from 2D to 3D, and we live in a 3D world. See, I can move in and out of this way too. Okay, so that is, let's look at the most classic case of 2D motion, and that's projectile motion. So let's start off with some definitions that we've already looked at. Remember, I started off with this. I want another piece of chalk, but okay, whatever. I already have this one. V average is delta R over delta T. Yes, that is also equal to V0 plus V over 2. Just like before, I can do that as a vector operation also. I do need a bigger piece of chalk. That one's small. That one's a little bit bigger. New piece of chalk. Okay. I can also define the acceleration as delta V delta T. But that's a vector. And that's all I need, really. From those definitions, I can get the following, just like before, I can get the following kinematic equations. R as a function of t is r naught, the initial position, plus the initial velocity times time, plus 1/2 a t squared. This is two equations in one, right? Because r has an x and y component, r naught has an x and y component, x and y, x and y. So this is really x as a function of t is x0 plus v x0t plus 1/2 ax t squared, and y as the function of t is y0 plus vy0t at the y plus 1/2 ay t squared. Time is not a vector, so it doesn't have a component. And then I have the other kinematic equation. V is v naught plus a t, right? That's a vector. And then the last one is actually not a vector equation because it's squared, but it's still the same. V squared equals v naught squared plus 2a. Actually, this one you should probably just do it in two dimensions because you can't square a vector. So let's call this x, 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 x minus x naught, vy squared, that's a naught, vy naught squared plus 2ay, y minus y naught. Those two are really most important ones. Okay, projectile motion. Let's look at projectile motion. So projectile motion is what happens when an object, here's an eraser, it's a little bigger to see, moves in the air under the only thing pulling on it is gravity. So there's no other forces acting on it. So if I toss this eraser in the air, we call it projectile motion from the time right after it leaves my hand to right before it hits my hand. Okay? My hand interacting with it, it's not projectile motion. So the initial velocity is the velocity it has right after it leaves my hand. The final velocity is the velocity right before it hits my hand. So for projectile motion, this same thing works, except that the acceleration is actually this. 0 x hat minus g y hat. It has no acceleration in the horizontal direction. It has acceleration of negative g in the vertical direction, just like we said before. We did vertical motion problems. Now we can just add in horizontal motion problems too. Okay. So because these things are separated, the accelerations are separated like that, we can treat projectile motion as a horizontal motion with no acceleration, 0 acceleration, and a vertical motion with an acceleration of negative g, and the only thing that they have in common is time. The time it takes to move in the x direction is the time it takes to move in the y direction. Let's look at this famous case, and I'll just sketch it out here. Suppose I have a cliff or a table, it doesn't really matter, and I launch a ball horizontally off like that. So it has some initial velocity in the x direction, v0x, and the y direction has 0 velocity. And at the same time, I drop a ball straight down. These two balls are going to hit the ground at the same time. If I drew the position of these every 1/100th of a second or something like that, it might look like this. Let's put it up here. So you'll see that they have the same y position, but this one's moving in the x direction also, and they will end up at the ground at the same time. This is how you can show for yourself that the horizontal motion and the vertical motion for projectile are completely independent. Let me solve the simplest projectile motion problem, and then I'll set up the complicated one, which is shooting this off at an angle. The simplest projectile motion problem looks like this. Suppose I have some ground, and I throw a ball with initial velocity v0 at an angle theta, and it goes like that. And I can write the following equations for the x direction. Let me first of all say, in the x motion, I'll break this into x motion. I can say my initial x, let's say, is 0. I'm going to start right there. My final x is over here, which I don't know. And then I have my initial x velocity, vx0, is going to be v0 cosine theta, right? Because if this is a vector, its x velocity is that part right there, which is the adjacent side, and that's my cosine function. I don't know the time. I do know this equation. X, the final x, is x naught plus vx naught t plus the acceleration, but it has no acceleration in the x direction, so that's it. If I know how long it was in the air, I could find out how far it went. Okay, now let's look at the y motion. In the y motion, its initial position is 0. Its final position is also 0. It's going to start here and land at the same y level. Its y velocity, vy0, is v0 sine theta, right? Because that's going to be this side right there, the opposite. And the kinematic equation I really care about here looks like this. y0 plus vy0 t minus 1/2 g t squared. Now, I actually can solve this for time and then use it over here. So if I solve this for time, I'm going to put in my value for y and y0. I'll leave vy0 just vy. I'll put in v0 sine theta. This equation becomes this. It becomes 0 equals v0, that's a 0, sine theta t minus 1/2 g t squared. Now I'm going to add this term to both sides. I get 1/2, that's a half, g t squared is v0 sine theta t. I'm going to divide both sides by t, and then multiply by 2 over g. So I get t equals 2 v0 sine theta over g. So that's the time it takes to be in the air. Notice that my units do work out. I have 2 doesn't have units. This is in meters per second divided by meters per second squared. The meters cancels, the 1 over seconds cancel, get 1 over seconds or seconds. Sine theta is just a ratio, it doesn't have any units. Now I can take that and plug in right over here, and I get x equals, it started at x equals 0, I get v0 cosine theta, that's my initial x velocity, times time, which is this. I don't want to run out of room. I think I'm right there. Let's move it over. X equals v0 cosine theta to v0 sine theta over g. So let's just go ahead and simplify that. I always have to look to make sure it's still on the board. X equals 2 v0 squared cosine theta sine theta over g. Now you can use your trig rules. If I have cosine theta times sine theta, that's equal to, and that, you don't have to do this, but it's 2 v0 squared sine of 2 theta over g. And you'll see this come up a lot. This is called the range equation. But be careful. This is not the final position of every mass, because it depends. This is only true if it starts on ground level and ends on ground level. Okay. But this says how far as it goes depends on the launch velocity and the launch angle, and assumes there's no air resistance. Let's set up a more complicated equation. I won't solve it the whole way, but I will show you why you'll need the quadratic equation. And I'm going to do some examples. So we're going to, this is just, we're just talking here. We're not solving problems. This is the chapter summary. Okay. Here is a more interesting problem. What if I launch it off of a cliff? So this is some height h, and I want to find out how far it goes x. Well, the difference here, the x motion is the same. I still have this. X equals x0 plus v0 cosine theta t. I still have that. In the y direction, I have this. The final y is 0. Let me write down the equation. Y equals y0 plus v0 sine theta t minus 1/2 gt squared. Now, the final y is 0, but the initial y is not 0, it's h. So I get this. 0 equals h plus v0 sine theta t minus 1/2 gt squared. I still want to solve for the time, and you can. You can solve this for a time, but you have a problem here. I have a constant term, I have a term times t, and a term times t squared. How do you solve that? The answer is the quadratic equation. So remember, if I have an equation that looks like this, a x squared plus b x plus c equals 0, in this case I'm dealing with time instead of x, then x is negative b plus or minus the square root of b squared minus 4ac, all of that over 2a. So in this case, this term is a, this term is b, that term is c. And so you actually get two solutions, two times, because you're saying what time does it get over here, and there's going to be one time, and there's another time going back in time over there. Math doesn't know about time not being going backwards. So you get a negative time too. You wouldn't use a negative time here. But then once you find that time, you plug it in there, you find out how far it went. And I'll do that problem for you, but I want to set that up. There's one more thing in this chapter, and that's that I don't really want to get in too much, but I want to be complete. But it's gets a little complicated. It's called relative velocity. So imagine that there is a car, a train car, and there's a person in the car, and the person throws a ball at 10 meters per second that way. But the train is traveling 5 meters per second that way, and there's a person standing over here on the ground looking at that. And there's no walls on this train, okay? I should tell you that. There's no walls. So what's the velocity of the ball if the person threw it 10 meters per second? Well, you could say in your mind, oh, it's 15. This person would see it as 15. This person would see it as 10. And the answer is velocity is relative. The velocity is relative to wherever you want to measure it from. So if I measure it with respect to the ground, it's 15 meters per second. If I measure it with respect to the train, it's 10 meters per second. What if I threw it back this way? Then it'd still be 10 meters per second with respect to the train, but this person would see it as negative 5 meters per second. Okay. So in general, we would like to write something like this. The velocity of the ball with respect to the ground is equal to the velocity of the ball with respect to the train plus the velocity of the train with respect to the ground. So with these indices here, it's going to help me figure everything out. So this is ball with respect to ground, ball with respect to train with respect to ground. If I get those two indices to match up, then you can think of them kind of canceling. They don't really, but that's how you know how to line them up. Okay. And I wrote these as vectors because imagine a way more complicated situation where the person throws the ball straight up with respect to the train. Like that. Then what would this person see it as? Well, you could still do it. The velocity of the ball with respect to the train would be in the y direction. The train would be in the x direction. And so the ball with respect to the ground would have an x and a y component. So if you're moving along this way, it gets launched up. The person over here would see the ball going like that. Okay. The person in the train would see it going straight up. And that's all I really want to say is that that equation does exist. Velocities are relative to your measuring reference frame, and you can switch between one frame and the other if the frames are moving with a constant velocity. This does have a lot to do with like what direction do you aim a plane if there's a crosswind, what direction do you swim across a river if you want to get to cross the other side. But they can get really, really, really complicated, and I don't really like them, so I'm not going to have them on the test. But that's in Chapter 2, and I'm just trying to follow along with Chapter 2. But that's Chapter 2. Oh my gosh, this is 42 minutes long. If you watch this whole thing, you should give yourself a double high five, because that was a long lecture. My fingers are tired from all that chalking. Okay, but I'm going to do some problems and stuff like that too, so don't worry about that. Read the chapter. The chapter is super important also. It has some PhET animations that I think are pretty good. So I would recommend you use those too. And that's that.